I've got 5 parabolas here that will all have different solution types in the quadratic formula. Specifically, the way that the values of a, b, and c come out of this discriminant. b squared minus 4ac are going to tell us whether we have 2 real or 2 complex solutions, 2 irrational or rational solutions, or even if there's just one solution. So b squared minus 4ac on that first parabola is going to look like this. b squared minus 4ac. That's 4, and that's 20. 4 times 1 times 5. Now 4 minus 20 is a negative number. So if you're taking the square root of a negative number, you're not going to get a real number. You'll get a complex number. At least 16 has a square root. So there will be 2 solutions. However, they will be complex rational numbers. Complex because it's negative, rational because 16 has a square root. X squared plus 5x plus 3 is going to have something else because 5 squared, that's b squared minus 4ac. Now we're talking about 25 minus 12. 25 minus 12 is 13. 13 is positive, so at least we're getting a real number, but 13 is also prime, which means we're not taking the square root of it and getting something rational. We will have 2 real irrational solutions to that parabola in the quadratic formula. X squared plus 4x plus 3, if we do b squared minus 4ac, this is going to be 16 minus 12. 16 minus 12 is positive 4, and congratulations, we have a positive number with a rational square root. We're actually going to have 2 real and rational numbers. 2 real rational numbers. Moving on down, x squared plus 4x plus 4. B squared is going to be 4 squared minus 4ac. Well, would you look at that? 4 squared minus 4 times 1 times 4. That's 16 minus 16. That's 0. If b squared minus 4ac equals 0, then this discriminant just doesn't appear. If that's gone, all that's left is minus b over 2a, and there's not 2 numbers anymore. One solution, just one rational solution. That is negative b over 2a. Okay, by process of elimination, I've had all my real solutions already, so I'm going to have one more complex one. Let's just see what it is specifically. B squared minus 4ac. B is 1 here, so 1 squared minus 4 times 1 times 2. Okay, that's 1 minus 8. 1 minus 8 is negative 7. Not only is 7 negative, but double whammy, it's also prime. Its square root will be irrational. So this will be 2 complex irrational solutions. Okay, knowing the types of solutions that all of these will be, you can actually start to find them now. I'm going to start with the easiest and then go to the hardest. The easiest is going to be this one with the one rational real solution. X squared plus 4x plus 4 will only have one solution, and we don't actually need the quadratic equation, the quadratic formula to tell us what it is, because this b squared minus 4ac is just gone. There's nothing there. And you'll know that you have this situation where the last term is the square of half of the middle term. I know that sounds a little convoluted, but if you have a parabola which is a perfect square, x plus a times x plus a, when you FOIL that, you end up with x squared on the left side, a squared on the right side, and in the middle, plus 2ax. So cut this in half and square it, you've got that. Half of 4 is 2. 2 squared is 4. And that means that you're going to end up with just one solution here. And as I said before, if b squared minus 4ac is missing from the quadratic equation, all you have left is negative b over 2a. That is the x-coordinate of the vertex. Negative b over 2a. Negative 4 over 2 times 1 is negative 2. So I'm pretty sure the vertex is going to be on this axis of symmetry. And I'm also pretty sure that if there's only one x-intercept, it's going to be the vertex. So if I turn on that graph, that should be not only the vertex, but also the x-intercept, and that is correct. So -2 is the answer to the quadratic equation here. That is the only x-intercept, -2. Okay, the next easiest one to do, the second easiest, would be the two real and rationals. So that would be the one directly above it. I don't need the quadratic equation again, because if I've got rational solutions, that means I could see which lines multiply together to make that parabola. That is, I want to find two numbers that add up to make 4, but multiply to make 3. I'm looking for two numbers that satisfy this condition. The sum, oh, sorry, that's going to be too far and I won't be able to see it. The sum of two numbers should be 4, but the product of those numbers should be 3. So are there any numbers that satisfy that condition? Well, sure. 3's only factors are 1 and 3, and if you add 1 and 3, you get 4. The numbers are 1 and 3, which means if I were to FOIL that pair of lines, I will get x squared plus 4x plus 3. Now, that line has a y-intercept of 1. This line has a y-intercept of 3. They both have a slope of 1, which means that this y-intercept leads to that x-intercept of -1, and this x-intercept leads, this y-intercept leads to this x-intercept of -3. Those are those two lines, x plus 1 and x plus 3. These values, -3 and -1, are the values that cause that to be 0 and that to be 0. In short, whenever this line is 0, that parabola is 0. Whenever this line is 0, that parabola is 0. And that's going to occur here and here. So if I turn that parabola on, I should see -1 and -3 as the two locations where the x-axis is intercepted. Those are the x-intercepts, -3 and -1. So let me write those down so I can move on. -3 and -1. If you were to plug A, B, and C from that parabola into the quadratic formula, you would get those numbers. It's just a little easier if you can quickly find two numbers that multiply to make 3 and add to make 4, and then take their opposites. Okay, now I am forced to use the quadratic equation simply because I'm going to get irrational and complex answers, and I'm not going to be able to just guess that one with my mortal brain. So I'm going to start off with the two real and irrational numbers. A is 1, B is 5, and C is 3. With the quadratic formula written here, I've left some blanks to quickly fill it in. B is 5, so 5 goes everywhere there's a B. A is 1, so 1 goes everywhere there's an A. And then C is 3, so 3 goes everywhere that there is a C. Right, so what do we have here? I've already done this actually. 25 minus 12 is 13. I think we already saw that. So this is going to be -5 plus or minus the square root of 13 over 2. And actually, I can't do anything now because 5 is prime, 2 is prime, square root of 13 is irrational. I can't simplify this at all. I might want to see this written in a different format depending on, what textbook you're reading or what teachers teach in the class. But either way, there's your answer. And so I will write that down. This is two real and rationals, -5 plus or minus the square root of 13, but all of that's over 2. Okay, it's only going to get harder from here because now I need to have some negative numbers inside that radical, and I will have some complex numbers as my solutions. But at least I don't need to go irrational yet because I've got two complex and rational numbers coming out of that one right there. Let's see how that goes. A is 1, B is 2, C is 5. B is 2, A is 1, C is 5. Okay, once again, I think I've already done this one. 4 minus 20, that's negative 16. So negative 2 plus or minus the square root of negative 16 over 2. Square root of negative 16 can be simplified because negative 16 has several factors which are perfect squares. Negative 16 is equal to negative, oops, sorry, I can't write that far over, you won't be able to see it. Negative 16 is equal to negative 1 times 16. So the square root of negative 16 is equal to the square root of negative 1 times the square root of 16. Well, that's 4, and this is I, the imaginary number. So that means that the square root of negative 16 is 4i. The square root of 16 is 4, but the square root of negative 16 is 4i. Right. Everything on the top is even. There's a 2 on the bottom. This can be reduced. 2 over 2 becomes 1, so negative 1 plus or minus 4 over 2 becomes 2, 2i. Negative 1 plus or minus 2i, that's what I get right here. Only one problem left. This will be the most challenging because it includes both complex numbers and also irrational ones. I'll have a negative number under that square root, and I will also have something I can't simplify under that square root. Let's see. X squared plus x plus 2. A is 1, B is 1, C is 2. B is 1, A is 1, C is 2. Right, so if I am doing negative 1 plus or minus the square root of, and again, we've seen this already, 1 minus 8, that's negative 7, over 2. Okay, that looks awful. It kind of reminds me of this one because that 13 couldn't be simplified and neither can that 7. But that's not a 7, it's a negative 7. It contains negative 1 as a factor. So we can take that out and call that negative 1 over 2 plus or minus I times the square root of 7 over 2. Again, which one of these you're writing, it's really just a matter of style. There might be some argument about which one is simpler, which one you just think looks better. Otherwise, as long as you're mathematically equivalent, come on. You're just being picky. Anyway, in terms of what that one looks like, I showed you the graph for a couple of the other ones, but what about when the zeros, when the x-intercepts are complex? Well, if I put that here, you'll notice that there are no x-intercepts. I'm sorry, let me take that back. There are no real x-intercepts. This x-axis is a real number line, and there are no real x-intercepts. Instead, if you extend this real number line into a complex plane, I need another spatial dimension to do that in. The vertical dimension is my y values, so I just need another direction, and so we might picture this parabola as extending out from the board or maybe into the board, and if it does, it has some shape where it has some sort of complex x-intercept somewhere out here in the plane. But this is just a cross section then, and we would just say, I guess it just doesn't have any, not any real ones anyway. So those are the graphs and the x-intercepts, if they exist, real, complex, rational, irrational, for 5 different parabolas with 5 different types of solutions in the quadratic formula.